And welcome back, this time to the Law of Cosines. Like the Law of Sines was an analog to the trig ratios for a general triangle, it's going to be the case that the Law of Cosines is how we're going to generalize the Pythagorean theorem. So remember for me the Law of Sines, which said the ratio of each side length to each sine of opposite angle for every set of things, right, for each ratio for everything on the triangle, those are always the same. So no matter how big the triangle is, the ratio not of every side, but rather the ratio of every side to the opposite angle and a sine, that stays the same. And that gave us three nice equations. We got to bring in sine of angles into the discussion for general triangles. We can't do it for we can't do as much as we did do with right triangles, with general triangles, but we can still do a few things. The Law of Sines gives us one such thing, and that's very lovely. We've worked with that a bit in class already. But now what I want us to do is try and figure out how to bring the Pythagorean theorem back into the mix. Right, we lost that too when we lost the rightness of our triangle. But there is still something we can do. And that something we can do is force there to be right triangles where there aren't. So here's our general triangle, as seen all the time, as drawn the way I like to draw it. Also with the usual conventions there, C is opposite C, A is opposite A, B is opposite B. And what we can do is, like we did when we were making the Law of Sines, we can drop a vertical. We can drop this altitude that is perpendicular with side B here. And what I'm going to do is I'm going to use the Pythagorean theorem on this triangle here, triangle ABD, or ADB, same one either way. I can do that because it's a right triangle. So C squared is not equal to A squared plus B squared, right? A is over here, B is over here, and B is this whole side length. It's not the segment from D to A, it's the segment from C to A. So I have to do a little bit of substitution here. I'm going to make H be the height of this altitude, so that's my vertical length there, and my horizontal length I'm going to call x2. The reason why I'm going to do that is because, well, I can split this total length into two pieces. Right, I'm going to let this length right here, from C to D, oh goodness, be x1. And I'm going to make the distance from D to A, the bit I need, x2. So there we go, that's our overall length. So by the Pythagorean theorem, this length here for C is equal to, well, in squared, is equal to h squared plus x2 squared. But that's not good enough. I want something using just the dimensions I care about. I want to turn that somehow into something looking a lot more like the Pythagorean theorem. And the way I can do that is with a little bit of substitution. I can look over here for angle C and say, okay, well, the sine of C for triangle BCD or BDC, whatever you want to call it, this triangle over here, the sine of C is opposite to hypotenuse. Sine of C is h over A. Now, whereas before, what we did with the Law of Sines, we looked at the sine of A being h over C, and we set h equal to h. But what we're going to do now is we're going to take h equaling A sine C and substitute it into the Pythagorean theorem. And also, we're going to do something similar for x2 here. Right? I could use cosine of C being x1 over A to solve for x1 in terms of A and C. And so that gives me now x1 is, let's see, it's what? A cosine C. So x2, the length that I care about, is over all B minus x1, so it's B minus A cosine C. Now hear me out. It's gonna work out, promise. Because when I square all this mess, when I square h, that means I'm squaring A sine C, I'm squaring all that. So A squares to A squared, sine C squares to sine squared of C. Then I am squaring x2. So B minus A cosine C is all being squared. And when I do that, I have B squared. I have A squared cosine squared C. But also I have this middle term, right? When you're squaring a binomial, when you're squaring this minus this, You FOIL that out, and you end up with b squared minus 2ab cosine c, and plus a squared cosine squared c. And then when we clean it up a little bit, right, I've got this a squared sine squared here and this a squared cosine squared here. I can factor out the a squared, leaving us just with sine squared plus cosine squared, which again is just 1, incidentally by the Pythagorean identity. So after reducing this down, I get c squared equaling a squared plus b squared, much like the Pythagorean theorem, but now with the added term for being in a general triangle. So it's a squared plus b squared minus 2ab cosine c. And unlike the Pythagorean theorem, this is always true. This holds for all triangles. But wait, you exclaim, you object. Once again, you have done this for an acute triangle. All the angles are less than 90 degrees. Is there a way to illustrate the law of cosines for obtuse triangles? And the answer is yes. Yes, you can. What you do is much like what we did before, except now when we drop our altitude, we're just not going to be on or in our triangle. So instead of subtracting out some length, I have to add that same length. But also, because theta here, that angle, that interior angle is now greater than 90 degrees, if I were to take the cosine of that, that would be negative. But I need distance to be positive. So I still end up with the same situation, right? Instead of sine squared here, I still have that, but instead of a plus b cosine theta, I still have to make it negative so that when I add that distance, I am actually adding distance. And so we end up via acute triangles or obtuse triangles always getting the same result. And again, that same result we had already to be c squared being a squared plus b squared minus blah, blah, blah. But also, it's true for every vertex. So once again, the law of sines being 3 equations, the law of cosines is now also 3 equations. So you pick any side length you want, and you square that thing. That is going to become, that's going to be equal to the square of one other side plus the square of the remaining side, and then minus the 2 product of each remaining side times the cosine of the opposite angle. So really, it's a lot to look at, but at the same time, the way I remember it is, okay, I want this side, I want a squared. Well, then what's going to be in the cosine is the angle opposite. It's going to be a. And so what goes everywhere else is b and c, the 2 remaining sides, one squared, the other squared, and then the product. Here I've got b squared on the left. That's what I'm essentially using the Pythagorean theorem around. And so what's going to be in the argument of cosine is big B, angle B. And then the a's and the c's get distributed around the rest of the equation. And similarly for c there. So it's very similar equations in much the same way that the law of sines was similar equations. And that's the law of cosines. These 3 equations, these 3 analogs of the Pythagorean theorem form the law of cosines. They are formulated, and again, just like how I used the videos in the law of sines to show the trigonometry at play, so too did I do it here. I want you to see where this is coming from. I want you to have a good visual and use the right triangle trigonometry to make more general trig. And in the next video, I want us to start using this to find unknown sides. So I shall see you then. I don't think there's a question this time. I think we're just going to get right into it. So take a minute, let this settle, and I'll see you then.